Hey there, everyone. We are going to begin working with the graphs of radical functions here. In this section in particular, though, we're going to give focus just to square root functions, and then later on we'll work to understand other types of radical functions, such as cube root functions or fourth root functions or whatever sort of nth root. So to begin right here, we need to understand where square root functions can kind of come from and compare them to things that we already know about graphs of functions. So where I want to start is I want to start with the graph of this right here, the relation in y equals x squared. So we know that that is the parent function or the main plain Jane function for the function family of quadratic functions. In quadratic functions, we know that we have the highest power on x is 2, of course, and they always make parabolas, right? So if we were to make a little table of values for this, right, and you were to plug in, say, like -4, if you squared -4, you would get 16, right? And then if you plugged in -3, you get 9. The square of -2 is 4. The square of -1 is 1. 0 squared is 0, right? So the reason why I'm making this table is so that we can find some ordered pairs that are going to be on the graph of this. -4, 16 is definitely on the graph, but the graph I have is only from -10 to 10, so it's not going to quite fit. So I'll graph at least -3, 9, -2, 4, -1, 1, 0, 0, and we could plug in, positive x values too. 1 squared is 1, 2 squared is 4, 3 squared is 9, etc. Right? So this is very familiar for us. We've graphed parabolas and dealt with them a whole bunch previous to this, right? So there it is. So what I'm going to do is I'm going to try to take this quadratic function and I'm going to try to find the inverse of this function. So we know that to find an inverse, inverses means that the inputs and outputs switch places in that relationship, right? So to find an inverse equation, you're just going to need to put in the input variable for the output variable. So plug in x for y, and then plug in the output variable for the input variable. So plug in y for x. So we end up getting the inverse equation to be x equals y squared. And then we could solve that equation to get the y variable alone if you undid the power of 2, which you could do by square rooting. And then, of course, do the same thing to the other side to keep the equation balanced. Now, because we are doing an even root to both sides, we're going to get plus and minus, technically. So we will get that y will be equal to plus or minus the square root of x. Now, for the sake of simplicity, because we actually got two different equations, basically, like you got y equals square root of x and y equals negative square root of x, I'm just going to focus on one of them for right now. So I'm going to make a table of values for just y equals the positive square root of x, okay? So we're going to kind of have our issue if we plug in some x values that are negative. So for example, if I were to plug in like -4 for x, then you would have to do the square root of -4, which is definitely, 2i. But if we were trying to graph this, we can't graph this on this graph because we're only graphing real numbers in a plane like this where x and y axes are just real numbers. So in order to really only graph points that are real, we're not going to really want to plug in negative x values. So I guess the smallest number that'll work to be able to show up on the graph is plugging in a 0 for x because we know that the square root of 0 gives us 0. So therefore 0, 0 is definitely going to be a point on the graph of y equals square root of x. So if you plug in a 1, we know that we can square root 1 and get 1. So 1, 1 is also going to be a point here. So if we were to plug in like 2 or even 3, we know that we're going to get some decimals there. So for example, the square root of 2 is 1.41. So you could plot the point to 1.41. And the square root of 3 is about 1.73. So you could plot about where that's going to be. But for the sake of just getting whole number coordinates, I'm just going to plug in only the ones that give me whole number coordinates. So if I were to plug in 4, we know that the square root of 4 is 2. So therefore I can plot 4, 2 is going to be on the graph, right? So really I'd only want to plug in, I guess, kind of perfect squares for x values to get whole number y values. So we would know that we would get 3, 4, 5, etc. The only other point that's going to fit on this negative 10 to 10 graph would just be the point 9.3, I guess. So it is continuous and it goes on forever, so I'll put an arrow. And so that right there gives us the graph of y equals square root of x. If you were to graph the y equals negative of square root of x, basically all that would do is it would just make the y values all become negative. So you'd still have like the same x values, but the y's would become negative, so it just kind of flips the graph upside down. And so this right here in the red would be y equals the negative square root of x. And so that gives us the graph of kind of that square root relationship. So I want to really emphasize for you guys here that because we graphed the inverse of y equals x squared, then what always happens with the graphs of inverses is that they reflect over this line y equals x. And so you should see very apparently that that is definitely holding, that this parabola really did just reflect over the line y equals square root of x. So like specifically you should be able to see like that this yellow half of the parabola became that yellow half when it reflected, and then this like tealish half of the parabola became that tealish half when it reflected over y equals x. So there's one slight problem though in terms of this graph right here, in that currently it's not a function as it stands, because if I were to draw a vertical line through it, it would hit there and then also hit there, which would make it not a function. So if we wanted to actually have something that's called the square root function, we would need to make it be a function. So in order to do so, rather than have both the plus and minus, then we're going to eliminate the minus and just make it y equals just the plus of the square root x, which means then that really I'm going to kind of erase the bottom half of this graph right here. And so now if we only had just the top half of the graph, it would actually be a function because it passes the vertical line test. And this is what we'll consider to be the graph of a square root function. So it's kind of just like half of a parabola, right? One half of it, but it's also kind of, tilted sideways rather than pointed upwards. So that is what the parent function of the square root function will look like. And so from this point forward, we're just going to look at graphing transformations of the square root function, shifting it upwards, downwards, stretching it, all that sort of stuff, things that we've done with other types of functions previously. So just right off the bat right here, whenever we're graphing radical functions, a radical involves doing some sort of an nth root. Could be a square root, but it doesn't have to be. It could be a seventh root or a cube root, whatever it might be. So what we're going to see happen in all of the examples of the graphs that we're going to be graphing in just a little bit here is just transformations, things that shift the graph up, down, whatever it might be. And so I'm just going to lay them all out right at the beginning here, and they are all going to connect to what you pretty much already know about transformations of functions. So inside of the root right here, I'm going to put the input variable x. So we're going to see that we could sometimes subtract or add some number that I'll call h inside of that root. And what that will actually do is it will result in a horizontal translation by that number of units. What that basically means is it moves the graph left or right that many units. And we've seen that happen before, right? So for example, like when we've graphed parabolas, if you have x plus 3, that quantity squared, we know that then that's actually going to shift the graph left 3 units. It always goes the opposite of what you think, right, when it moves left or right. So when it's plus 3, it's actually going to go to the left 3. So that's going to occur for us with these radical functions as well. And then if you add some number that I'll call k, turns out that that number is just going to be a vertical translation by that number of units, by key units. So that just means it's going to move the graph up or down that number of units. So we've seen that happen with other graphs as well. And then if you multiply the radical by some number a in front, that just stretches or shrinks the graph. So that's just going to be some vertical stretch or compression factor. And we'll see how that kind of plays out a little bit later on. And then the only thing that we're going to worry about is you could also make the number a in front also be multiplied by a negative, and really what that's going to do is it's just going to flip the graph upside down, basically, which we consider to be a reflection in the x-axis if it reflects over the x-axis when it does reflect upside down. So those are all the things that we're going to see in combinations of those elements. So I'm just going to break that apart in terms of the individual transformations that we see first, and then we'll look at examples that mixes all that stuff together. So I'm going to focus into these first couple examples right here, where we're going to look at what the graphs of y equals the square root of x minus 3 looks like, and then also what the graph of y equals the square root of x plus 2 looks like. So just for reference, I'm going to first of all graph the parent square root function, y equals square root x first of all. So what we know that to look like is the following. You'll have like these points because we know that the square root of 9 is 3, right? Or the square root of 4 is 2, the square root of 1 is 1, etc. So we get this kind of hook shape, half parabola, turn sideways thing, right? Okay, so this graph right here that's in the red text is y equals the square root of x, but then minus 3. So all that that's really going to do is it's just going to shift the graph down 3 units when you're basically just subtracting 3 from all the y values, right? So I haven't introduced a term quite yet. So this point right here, which is kind of like the tip of the hook shape, we're actually going to refer to that as the end point of the graph. So like previously when we've talked about, parabolas, we would call the tip of the parabola the vertex. But this point really, we don't usually call it a vertex. Some people might. But for the most part, we're going to refer to that as being the end point of the graph. So to graph, I'm just going to move that endpoint down 3 units, which would bring the endpoint to be right here. And then I can just follow the same pattern of going over 1 and up 1 because the square root of 1 is 1. And then if I go back to the endpoint and I count over 4 units, then I can go up 2 because the square root of 4 is 2. And then again, go back to the endpoint, and from the endpoint count over 9 units, and then you can go up 3 because the square root of 9 is 3, etc. Right? So you could keep going if you had a bigger graph to work off of, like you go over 16 and then up 4, but we're out of room, so this is pretty much all that we can fit on. So that would be the graph of y equals the square root of x and then minus 3. So you get the gist that, okay, if it's just plus 2, it's going to move the graph up 2, right? So move the endpoint up 2 units, and then you can go over 1, up 1, and then over 4, square root of 4 is 2, and then over 9 and up 3. And then that right there is going to give you the graph of y equals the square root of x and then plus 2. Awesome. All right, then I'm going to take a look at these couple of examples right here. First of all, I'm just going to quick sketch out y equals the square root of x so that we can reference how these transform functions compare to the parent function. All right, so the first one right here is to graph y equals the square root of x plus 5, but the plus 5 is contained inside of the radical. So if it is plus, it goes the opposite direction what you would think. So it does move the graph left if the plus or minus is happening on the inside, and it's a plus, it'll move left 5 units. And then because this is the inside, it'll move it horizontally as well, but minus will move it to the right that many units. So it's going to shift the graph right 1 unit. So if I were to graph the first one, the one in the red right here, the square root of the quantity of x plus 5, you just move the left endpoint of it 5 units to the left, and then from that endpoint you can go over 1, up 1, over 4, up 2, over 9, up 3. We can almost fit over 16. I think it hits right there, and then up 4. So something like that, and then if you just connect all those dots and make that little hook shape like that, that'll be the graph of y equals the square root of x plus 5. And then for the one in the blue right there, for the y equals the square root of x minus 1, you can just go to the right one. So you're going to start at that ordered pair 1, 0 then. And then from the endpoint, go over 1, up 1, over 4, up 2, over 9, up 3, etc. So it's just a tish to the right of that parent function that's in the gray there. All right, so those examples show you some vertical and horizontal translations, just basically shifting the graph. So the next thing I want to take a look at is what happens when we are multiplying the root by a number, and what happens is we get some stretching and shrinking. So whenever this number that multiplies in front of the root is something that is like bigger than 1, which is the case with 3, we get a stretch of the graph vertically. So we get a vertical stretch by a factor of 3. And then if the number that you're multiplying by is less than 1, you get what we call a compression vertically of the graph. And so we'll see examples of both the stretch and the compression here. First of all, let me graph the y equals square root of x, so we can kind of compare how these graphs will look like relative to y equals square root of x. All right, so there's y equals just square root of x. So what's going to happen with the first graph, so y equals 3 times the square root of x, is you're just going to times everything by 3, right? So I think it's best if you just make a table of values so you can kind of see what's going to happen right here. So if I normally just plug in x values and then I get y equals just the square root of x, we know that we're going to get this table of values to hold, because if you square root 0, you get 0. The square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3, etc., right? So y equals 3 square root of x should really just take the square root of x, which is really all of these values, but then just times them all by 3, right? Which means then that this y value gets times by 3 to become 0, and then this y value gets times by 3 to become 3, and this y value gets times by 3 to become 6, and that y value gets times by 3 to become 9, right? So the points in blue, or these blue columns right here, are the x and y points that we're actually going to plot. So really, this is kind of how I think about it and understand it, is that if I know that I'm going to still start at the same end point, okay, if I go over 1, normally I would go up 1 because that's the square root of 1, but it's times by 3, so I'm going to go up 3 times higher than 1, right? So then if I go over 4, we normally would go up just 2, because that's the square root of 4, but it's times by 3. So instead of going up 2, we know that 2 times 3 is 6, so I'm actually going to go up 6 units and land right there. And then if I go over 9 units, normally the square root of 9 is 3, but since it's times by 3 in front, then 3 times 3 is 9, so I'm actually going to go up 9 whole units and land myself right there. And so then by connecting those dots right there, we do get a good, nice sketch of the graph of y equals 3 times the square root of x there, okay? All right, then I'm just going to put those dots back on there. Okay, perfect. So for the y equals 1/2 square root of x, basically kind of go through the same thought process. I'm not going to make a table of values for this, but it's going to start still at 0, 0, so there's going to be the endpoint of the graph. So if you go over 1, normally you would go up 1, because that is the square root of 1, but since it's multiplied by 1/2, you're only going to go up 1/2 of 1. So you just need to go up just 1/2, which means you're just going to kind of go right there, kind of halfway, right? And then if you go over 4, normally you would go up 2, but if you go 1/2 of 2, that would be just going up 1, right? So we're going to have a point right there. And then if you go over 9, we know that the square root of 9 is 3, but you only want to go half as far as 3. So you only want to go up 1.5. So then that right there will give you the graph of y equals 1/2 square root of x, right? So really, just vertically, you're going up half as far as you normally would, right? So those are some examples of vertical stretches and compressions. And we'll follow up more with that in just a little bit. And then finally right here, this is just acknowledging y equals the square root of x versus y equals negative square root of x. So basically, y equals square root of x is just the parent function right there. That's y equals positive square root of x. And so whenever you put a negative to multiply in front of the root, that just reflects the graph upside down. We actually did kind of graph this earlier as I was introducing some stuff. And so this graph right here would just be negative of the square root of x. So just flip it upside down, basically, right? All right, so now that we've looked at all of those individual things, so here we looked at vertical translations, and here we looked at horizontal translations, and then here's some vertical stretching and compressing, and then reflecting over the x-axis. We want to be able to mix all these individual things together. So that's what we're going to look at here. So in this first example right here, we're going to graph this function right here. So you can see that compared to just y equals the square root of x, there's a lot of things that are done differently here. So I'm going to focus on these couple of things here first, because I know that those couple of numbers are just going to move the graph left and right or up and down. So starting with that -3 right there. So anytime we're subtracting or adding something inside of the root, we know that this is going to be a horizontal translation. So in other words, it's going to move it left or right. When it's minus, it goes the opposite of what you would think. So it actually goes to the right. So right here, it does say that we're to describe the transformations of the graph of the parent function, y equals square root of x, that yield the graph of what we're graphing right here. So one thing that's going to happen is we're going to move 3 units to the right. The technical term that we use for that is to translate y equals the square root of x 3 units to the right. So that'll be one thing that we'll need to do. This plus of 1 will definitely result in a vertical translation. Because it's plus, it does go the same direction as what you always think, so it's going to go up. So we still call that a translation as well when you're just moving the graph, but it just moves it a different direction. In this case, it'll move it 1 unit upwards. So there's a couple other things that are happening here as well. You can see that there is a negative multiplying in front of the root. So what that's going to result in is it's going to result in flipping the graph upside down. Technically, we say that's going to be a reflection in the x-axis to flip the graph upside down. And then finally, you have this 1/2 in front. And so that's going to vertically compress whenever that number is less than 1. So it'll vertically compress by a factor of 1/2. Okay? All right, so I'm just going to kind of do this a few pieces at a time to show you how this results in the graph of what we're trying to graph right here. So I'm just going to start with y equals square root of x, and we're going to change little pieces of it at a time. So if I graph y equals square root of x, that's just the parent square root function. That's going to look just like this, right? Beautiful. All right, so what I'm going to graph next, and I'm going to pick a different color for this, how about like orange, is I'm going to graph y equals the square root of x minus 3 and then plus 1. So I'm incorporating that -3 inside of the root and then the plus 1, but I'm going to ignore the negative and the half for right now. Because what's going to happen is this should move the graph to the right 3 as well as up 1. So I'm going to take this endpoint right here and move it right 3 and up 1, which moves it to that point right there, which would be the endpoint. And so from there, I'm just going to then go over 1, up 1, and then back from the endpoint over 4, up 2, since the square root of 4 is 2, and then over 9, and up 3 would be somewhere over there. So that right there would be the graph of y equals the square root of x minus 3 plus 1, right? So now what I'm going to do is I'm going to graph y equals -1/2 of the square root of x minus 3 plus 1. So there's going to be a couple things that happen now. So it's going to be reflected upside down because of the negative, but then it's also going to be compressed by 1/2. So what's going to happen is the endpoint should remain as it is, right? So when I go over 1, rather than go up, I'm going to go down, but I'm not going to go up 1 whole unit because it's multiplied by 1/2. So I'm only going to go down 1/2. So that little point right there would be a point that's going to be on the graph. And then from there, I'm going to go back to the endpoint, and then I'm going to count over 4 units. And then instead of going 2 units vertically, I'm only going to go half of that, which is just to go 1 unit. Then I'm also going to go down because it's negative, so then that's going to be another point that I'll use. And then I'll go back to the endpoint and I'll count over 9 units. And then instead of going 3 units vertically, I'm going to go 1.5 because that's half. But I'm also going to go down, so somewhere like right there would be going down 1.5. So then if I connect those points and I draw an arrow, that is my final graph, right? So what you see in the blue right there is the graph that we wanted to have graphed, okay? So, as you're graphing these and practicing this and such, right, ultimately you should hopefully not have to do all of the tiny steps that I did, but hopefully can just kind of do it right away from the beginning and the get-go, okay? So I'm going to try to show what I mean by that in the other examples just a little bit. So there's a couple other things that we want to make sure that we can identify, and that would be the domain of the graph, as well as the next question down, which is the range of the graph. So what we're looking at here is the blue graph. And remember that the domain of the graph is the set of all of the inputs. In other words, all of the x's in this graph. So it does turn out that actually 3 is the smallest x in this graph. But then all of the x's in the graph go onwards to infinity. So all x values that are equal to and greater than 3 are in the domain. Okay? Clearly, we don't have any negative x's or any x's that are 0, 1, 2, or 2.99 or anything, right? So just at 3 or higher. And then in terms of the range of the graph, remember that the range is the set of all of the outputs of the graph, which would be the y values in the graph. And so you can actually see that right here at 1, this is kind of the highest point of the blue graph, right? We're talking about just the blue graph. The blue graph will never go higher than 1, but it then hooks downwards, okay? So that part of the graph, it'll never flatten out. It'll never just be perfectly flat. It's always going to keep pushing down and down and down and down and down, which means that it will get to lower and lower and lower and lower and lower y values. It grows more slowly, of course. It'll take forever to get to super low numbers, but it will keep going down forever. So that means that all of these numbers that I just circled there are in the range, which is basically all y numbers that are at 1 and lower. So y being equal to or less than 1 gives us the range of this graph, the set of all of the outputs in that relationship. All right, and then we're going to jump down to this next example right here. You can see there's some green text around this to emphasize what we're trying to graph here. So for this graph right here, you can see that the -6 is kind of just in a little different spot, right? So if you thought of this graph as being y equals 4, a positive 4, and then x plus 1, and then -6, it'd be the same sort of thing, right? So what's going to happen with this graph is because there's a plus 1 inside of the root, we're going to have a left translation of the graph by 1 unit. And then because we're also subtracting 6, that's going to be a vertical translation downwards. So we're going to have a downwards translation by an amount of 6 units. And then finally, there's also a 4 times it in front. So since 4 is bigger than 1, that's going to result in a vertical stretch of the graph by a factor of 4. Okay? So what I'm going to do always when I'm graphing square root functions is I'm going to graph the endpoint first of all. So since I know it's going to go left 1 and down 6, I know that the end point of this graph is going to happen at -1, -6. So I'm going to go ahead and plot that point, which would be at -1, -6 right there. It'll be the end point, okay? If I were to just graph kind of a normal square root function that's not stretched or compressed from that point, I'd know that I would just go over 1, up 1, and then go over 4 from the endpoint, up 2, and then over 9, and up 3, right? So that sort of graph would not be stretched or compressed or anything of that sort. So the reason why I'm graphing this here is so that you can compare to when it's actually stretched, in this case by a factor of 4. Because what should happen is that if I start at the endpoint and I go over 1, rather than go up 1, it's going up 4 times as much. And so 4 times 1 is 4, so I'm going to count up 1, 2, 3, 4, right? So then if I go over 4, we know that normally here it's going to go up 2, but I need to times that by 4, which is 8. So I need to actually go up 1, 2, 3, 4, 5, 6, 7, 8. So right there would be 8 higher. And then if I were to go over 9 units, normally we'd go up 3, but it's stretched by 4. So 4 times 3 is 12. So I would count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So connecting those dots right there would be the final graph that we want to have graphed then, right? All right, and then for the domain of this graph, the domain is the set of all the x's, right? So it looks like from -1 and then higher is all of the x's that show up in this graph. So that means that x is equal to or greater than -1. And then in terms of the range of the graph, that'd be all the y values. So it appears that this green graph has the lowest point right there, and then it does stretch upward forever from there. So at the lowest, it's at -6, and then it goes higher. So that means that all the y values hit -6, but then also go higher. So y being greater than or equal to -6 gives us the range of that graph. Okay. Yeah, and then this last example right here, there's kind of a little fancy trick that's going to happen right here that you would have no reason to know about, but it's just something kind of cool that pushes you a little bit further in understanding some relationships that we could apply right here. So the reason why this one would be ungraphable, based on your understanding so far, is because it's a 9 times in with the x, right? And then plus 18. So it's not going to shift the graph to 18 units. Because there's also a 9 in front of the x. But so there's a little trick that I'm going to do right here. And so I'm going to actually factor the inside of that expression. So by factoring, you can see that the 9x and 18 have a greatest common factor of a 9. So I'm going to write that as 9 times the quantity of x plus 2. And then what we know to be true about radicals is that if you have two separate things that are timesing with each other, right? So like if m times with n under a root, it's always true that you can write it as the product of separate roots of those things, so m times n. So I can do that here. I can write this as the square root of 9, and then the square root of x plus 2, and then the power of that is there's actually the 9, which is a perfect square, so then if I square root 9, I actually get 3 times the square root of x plus 2, and so now this right here is very graphable based on our understanding, because now there's just a 1 in front of the x. So yeah, all that's really going to happen here, my friends, is because there's a plus 2 inside of the root, it's just going to shift the graph left 2 units, and then it's also going to stretch the graph vertically by a factor of 3. And so yeah, so all I'm going to do here is I'm going to find the endpoint first of all. So since it's going to shift the graph left 2 units, I'm going to go to the left 2 from the origin. So that right there would give me the endpoint. And then let me graph just going over 1, up 1, over 4, up 2, over 9, up 3, right? So that would be if it's not stretched or compressed. That way we have a reference, right? So if it's times by 3, then you're just going to go up 3 instead of going up 1, and then instead of going up 2, you're going to go up a total of 6. And then instead of going up 3 times 3 is 9, so 4, 5, 6, 7, 8, 9. That's where that would land. Then this right here, that orange graph would be kind of be your final answer for what the graph of that looks like. So I already kind of listed out the transformation. So it's a left translation by 2 units, right? And then we also said it was going to be a vertical stretch by a factor of 3. And then just a couple things to identify as well, right? So the domain of the graph, all the x's, so the lowest x is at -2, and it goes on, so x is equal to or greater than -2. And then the range of the graph is the set of the y values. So the lowest it ever gets to is right sitting on the x-axis, which is at a height of 0, and then it goes upwards from there. So y being equal to or greater than 0 gives you the range for the graph there. Awesome. All right, just the last few things to kind of tackle right here. Here's an example where we're going to write an equation for the square root function that is shown in the graph. So whenever you're dealing with functions and try to write a function, it's nice if you try to write it in this general form of transformations where you have maybe a reflection, a stretch or a compression, a horizontal translation, and a vertical translation, right? And think about all those things. And then the reason why I put this square root is because it told us it was a square root function, right? So what I'm going to try to find is I'm going to try to find, first of all, kind of the h value and the k value, the horizontal and vertical translations, which you can easily do if you find where the endpoint is relative to the origin. So relative to the origin, we had to move this far to the left, which would be going over just a little bit more than 3. So we went to the left 3.5, and then we went up 1, 2, 3, 4, and it looks about 4.5, right? So also up 4.5. So because of those features then, we should know that underneath the square root, when it goes left, think opposite, right? There has to be a plus underneath, and then 3.5, that would force the graph to be translated to left 3.5. And then for it to go up, you would have to plus outside of the root, and then it went up 4.5, so you could put plus 4.5 right there, right? Yeah. And then you can also see that the graph, it's not hooked upwards, right? It's actually hooked downwards, which is negative. So we also know that there is going to be some sort of a negative number times in front of the root. So if we wanted to know what number this might be, whether it's a 1 or a 2 or a half or something like that, you'd want to look at the vertical distances compared to y equals square root of x. And here's what I mean by that. So if this is where the end point is, when we think about a square root function, normally if you go over 1 unit, it's going to vertically move 1 unit. So I'm going to go down. And then if you go over 1, 2, 3, 4, it should go down 2. And then if you go over 1, 2, 3, 4, 5, 6, 7, 8, 9, normally it should go down 1, 2, 3, and land right there, right? So normally, if there was just a 1, right, in front of the square root, or a negative 1, it would go like that. So clearly that's not the case, because clearly what's happening here is it's gone down 1, 2 and a half, right? And then here it's gone down 2, 3, 4, 5. And then here it's gone down 1, 2, 3, 4, 5, 6, 7 and a half, right? Compared to going down just 1, going down just 2, and going down just 3, right? So when you compare 1 to 2.5, it's 2.5 times higher, and it turns out that if you also multiply 2 by 2.5, you get 5, and if you multiply 3 by 2.5, you get 7.5. So because vertically it's going 2.5 times further than normal, then we would know that this number right in front right here has to be a 2.5 with the negative in front. So that right there is the equation for that square root function. Yeah, and then the last couple of things to address right here is being able to find domain and range for square root functions. Now, this is something that you should be able to do without actually graphing the functions. So when you think about domain, you have to think about the set of the inputs, right? And then when you think about the range, you have to think about the set of the outputs, okay? So the first thing that we're asked to find the domain and range for right here is y equals square root of x. So there's some things that you can maybe think about that can be really helpful. So one thing you could think about here is just think about what the graph looks like. So in your head, or if you want to just kind of sketch it out too, you could think, okay, so here's my graph. So I know that y equals square root of x goes like this, right? So then when you think about the domain, you think, okay, so it's only positive x values or 0, right? So my domain has to be things that are equal to or greater than 0, right? And then you think about your range, you can look at the graph and say, okay, it's only positive, right, or 0. So it's got to be at 0 or higher. So my y values are greater than or equal to 0, right? Yeah, so similarly, you can think a similar thing right here. Like if I have y equals the square root of x plus 3, right? Think about what the graph would look like. Okay, so what's going to happen, right? So I know what square root of x looks like. So if it's plus 3, right? Think to yourself, okay, that's going to go left 3. So it's going to go like this, but then it's just going to be hooked like that, right? So when you think about the domain is going to be all the numbers at -3 and higher, right? So x is going to be equal to or greater than -3. But then the range will still be at 0 and above, like the previous graph, since it sits still on the x-axis. So that gives you the range, right? And then this example right here, you've got negative in front of the square root x and then plus 8. So you know that this is going to move the graph up 8 if it's plus 8 outside of the root. But then this is also going to make it go upside down and reflect it as such. So if you move up 8 and then it reflects upside down, it's still going to hook to the right, but it's going to hook in that direction, right? So now when you think about the domain, you think about the x's. So the smallest it gets to is 0 and then goes higher. So the domain is going to be all numbers at 0 and higher. And then in terms of the range, it looks like this is the highest point, and then it goes lower because it hooks downwards. So it does turn out then that equal to or lower than 8 are all of the y values since it goes down forever. And then finally, one last example to kind of think about here is this guy right here. So because of these couple of numbers, which I'll address first, we know that the graph is going to go to the right 7. When there's a minus inside, it goes to the right. And then when there's a minus on the outside, it goes down. It'll go down 3. So if you go down right 7, down 3, you'd have an endpoint that's right about there. And then we can also see that there is a negative in front and also a -2, which makes it get stretched a little bit. So it'll be kind of going down a little bit faster, going down because it's negative. So it'll look something like that, right? So the domain would have to be these x numbers from there and on. And so we know that this is going to be at 7, so this went to the right 7. So at 7 and higher would have to be the domain of that. And then for the range, it looks like right here, and then lower is going to be all the y values. And so we know this is going to be a -3 because it went down 3. So all the y values that are equal to and lower than -3 gives you the range of that function.